I should try to forget.
I think now just check now. Check now, check now, check now. Okay. Yeah. Now you guys, can you guys hear me?
Yes, sir.
Okay.
Yes, sir.
Cool. So let us start. Let's not waste time. Cool. So today we are going to just do a little run through about how to use FFTs. Okay. So before we get into this, have y'all anyone heard of this before? Apart from me talking about it, if you guys have done live sound class and stuff like that. Anyone aware of, has any idea what we're going to do today? Yes or no? You can just switch your microphones on and speak to me. Any idea? If you don't have any idea, you can tell me no. If you have any idea, then great. Cool. I'm assuming none of you all know anything much about this, so let's dive into it. So what we're going to do today is we're going to, we have studied decibels, right? All of us have studied a little bit of decibels, so we know some basics about how to measure audio in air, right? So we are going to concentrate on this particular small part of it, like how to measure audio in air and what are the applications of it, right? So to start with, let's try and understand what exactly is measurement. Any idea? Can anyone tell me? It's a very basic question. Anyone knows what exactly is measurement? Not in terms of sound, in terms of anything. In your own words. Guys, you guys need to communicate
So
with me.
measuring something like and the quantity which we actually don't know with something that we know.
Yeah, you're pretty much right. So in simple words, basically, what is measurement is that you just take some physical something physical, right? For example, it could be anything. It could be length. Okay, use a ruler to measure length, right? So what are we doing is we are taking that physical quantity and we are associating a number with it. Same thing is with speed as well. Okay, if you want to know how fast you're going, you take that physical quantity and you assign a number to it. Similar thing with weight as well, right? If I tell you to go out and get some tomatoes, what is the first question you'll ask me after I give you this statement is how much, right? So I will tell you, okay, fine, get 1 kg, get 2 kg. And that we have associated 1, 2, or 3 with the weight of the tomato, okay? So that is what measurement is in a very broad sense, okay? And depending upon the field you're working, or the field of science you're working in, those measurements keep changing. Is that clear? Everyone on the same page? Any
Yes,
doubts
sir.
here? Okay, cool. So next up, how do we use measurements in the audio domain? And we are now only going to talk about one small part of it. We are not going to talk about electronic measurements. We're going to only talk about acoustic measurements and where can we use all this stuff. Okay? One of the main things is to measure this arbitrary term called loudness. It's very arbitrary, okay? Because loudness is subjective. So we can measure, say we can measure loudness in terms of SPL, in terms of whatever it is, okay? We can measure, we can use these measurements to do time alignment for speakers. We'll be talking about time alignment in a bit, okay? We can check the acoustical response of a room. Do you all know what is an acoustical response of the room? Anyone, any idea? Okay, RT60, real-time analysis. These are few things we can do if we know how to measure stuff, if we know how to use the softwares, if we know how to use measurement as a whole. Any doubts here? You all know what is RT60, right? You all know what is real-time analysis? I'm sure an RTA, most of you might have used at some point. You might have switched on an EQ and logic or an Ableton and seen one wiggly line across the screen that keeps moving as you play some audio through it. That is real-time analysis. That is an RTA. Okay, we'll be talking about that. Any doubts here? Okay, next up, let's understand what measurement in audio actually means. Okay, there are two types of measurements in audio. One is acoustical measurements, the other is electronic measurements. Now, you might have learned about this in your decibels class. You might have learned about dBSWL, dBSPL. You might have learned about dBV, dBm, dBu, right? Do you all remember what all these terms mean? Anyone
Yes, sir.
can tell me anything about this? Now, why do I say acoustical and electronic measurements? Can you just, this you have already learned in class, so can you all tell me the difference between acoustic and electronic measurements? How are they different from each other? It doesn't matter, I don't need definitions, you can just give me your own understanding basically.
Acoustical measurement says what actually we hear, but the electronic measurement says how much voltage or current is passing
Exactly.
through.
So acoustical measurements are basically done in air. Okay, we are measuring sound pressure level, we are measuring power level. Okay, and in electronic measurements, you're measuring voltage, you're measuring electronic power. Okay, so it depends. Now, SWL and dBm, both of them measure power. So can anyone tell me what is the difference between these two? I just give you the answer in the previous statement. Okay, so SWL is basically the power that is generated in an acoustical environment, whereas dBm is the power of a particular device. It could be an antenna, it could be, you know, whatever electronic device. Okay, so we are going to be concentrating only on acoustic measurements, and for the next 5 to 10 minutes, we'll be talking mostly about dBSPL. Is that cool? You're good?
Yes, sir.
Okay. I went too ahead. Okay. dBSPL or sound pressure level. All of us know what it is. Okay, it is basically pressure changes are triggered by any sound that is generated in an atmosphere, in any kind of environment. Okay, in a medium, when you create some sort of a impulse, it kind of triggers a pressure wave. Okay, our eardrum kind of reacts to that pressure, and that's why it moves in and out, and because of that we can hear what we hear. Okay, distance from the source plays a very important role in SPL because of something known as inverse square law, right? How many of you remember inverse square law? Anyone can tell me basic definition of it? Okay, so simple thing, we know 6 dB drop as you double the distance. Okay, now what happens exactly? Now let's forget about audio for just a minute and think of light. Okay, say you have a light source and the light source is emerging, and the light source is basically sending some photons of light. Okay, some light particles are passing through a medium. Okay, now what happens is, if you say use some sort of a screen, okay, of a dimension, say use a square screen, okay, and you use a square screen in such a way that all the light coming out from the source shines that entire area of the screen. There's no light that is leaking outside. Okay, you mark that distance. Then you go twice that distance. Say if you're standing at 1 meter, you go at 2 meters. Okay, and then you try to use another screen to shine that, basically to block all the light. Okay, that screen will be much bigger. Okay, and the thing is, as you go further and further away, the screen area keeps on increasing. So when you think of it in terms of audio, if you think of audio, it's basically a spherical wave that kind of it is emitted from the source in a spherical nature. You take one small part of it, you see how many audio waves are passing through that part, and when you go double the distance, with the same amount of audio intensity that is passing through, that audio intensity will have to cover a larger area. Okay, and hence the intensity drops. So as you keep doubling the distance, the intensity keeps dropping. Okay, this is not a real world scenario. This is, you can call it a theory, but in the real world, what happens is, because we are dealing with a lot of obstacles, we're dealing with the ground itself, which also reflects certain frequencies. We're dealing with walls, we're dealing with the ceiling. If you're in a room, all that will kind of also play an effect on it. So you approximately get a 6 dB drop with every double of distance. Okay, so that's what you need to remember about SPL, and as you keep doubling the distance. It's very important when you're doing live sound and something, and especially when you're doing installs and stuff. If you want to get into line array technology and all, it all works on the principle of this. So they're trying to reduce the amount of signal that is dropping over distance. Okay?
Yes, sir.
Hold on. Yeah. Next up, this SPL is basically not absolute. Okay, just we saw in the inverse square law, it is not absolute. Okay, because as you keep moving away from the source, the signal keeps dropping. But it is not as simple as that. Okay, of course it keeps changing with respect to the distance, but this SPL also is frequency dependent, and that's really weird because say suppose you have you have a molecule of air that is that has a frequency of 1,000 hertz. Okay, it is moving 1,000 times in a second. Okay, at the same time, if you play a frequency of 100 hertz, it basically that 1,000 hertz will start riding on that 100 hertz wave. So when you're taking the reading, your SPL, what reading you take is also going to increase. Okay, but it's not going to increase linearly. So it's also frequency dependent. Okay, it also depends upon your environmental conditions. Your temperature changes SPL, humidity changes SPL, elevation changes SPL. Okay, how does it change? Any idea? We might have discussed this in live class for those of you guys who have done live sound. So when you have a humid atmosphere around you, what happens is there is water molecules in the air, and that makes the air a little more heavier. And when the air is a little more heavier, the high frequency finds it difficult to keep resonating, and that's why you get a quicker signal drop in the high frequencies. Temperature, what happens is if you're in a cold environment, the air is trying to condense because of the temperature being lower. Okay, and hence it's like being packed in a Mumbai local or something, where there are too many people standing around you and you're trying to move, but you can't move. You can't move as much. Okay, but as the temperature increases, the distance between the molecules of air increases. Hence, the molecules that are resonating in air can resonate for a longer time. Okay, elevation, of course, the pressure itself changes with elevation. As you go higher and higher from the surface of the earth, the pressure starts reducing. Okay, so that will also take a toll on the SPL measurement you're taking. Is that clear? So what we are dealing with sound is a very, very complex, we are dealing with very complex data. Okay, hence we require some sort of a proper algorithm to kind of do all these measurements for us. Okay, we cannot sit with pen and paper and just calculate everything. We can, it'll just take us too much of time. Okay? Weighing scales. Anyone remembers what is that? You all can answer while I just take a sip of water. Now, whatever we are speaking about, right, we are going to also listen to some stuff in a bit. So now weighing scales, we spoke about, we all know that we hear frequencies from 20 hertz to 20 kilohertz, right? Anyone can hear more than that or less than that?
No, sir.
Correct. So we all hear frequencies from 20 hertz to 20 kilohertz. But we also know Fletcher-Munson curve, right? That we don't listen to all the frequencies at the same level. Do we hear 50 hertz as loud as 1K? No, right? So we'll come to this point in just a bit. First, let's see what are the weighing scales. We have Z weighted, we have A weighted, we have C weighted. Now there are many more weighing scales, but for us, these three, actually rather two of them are very important. Z weighting means there's no filter added on it. Now I'll tell you what filter is and how these scales are used. Now this is a graph of a A-weighted scale. Okay? You all can see the screen clearly, right?
Yes, sir.
Can you see where the filters are? You can see approximately, say around at, somewhere around at 4 or 5K, it starts dropping off. It's not exactly, it's not to scale, but it'll give you an idea. But and somewhere below 500 hertz or something, it starts dropping again, right? There's a high pass filter and low pass filter added on. So what are these scales? Now see, there are a lot of different frequencies of sound. There are frequencies of sound that are even below 20 hertz and even about 20 kilohertz. Even within that human listening range, do we need to measure everything? If we cannot hear all frequencies at the same level, does it make sense to measure all of them at the same level? Yes or no? If we cannot hear 50 hertz as loud as 1K, does it make sense to measure 50 hertz with the same intensity as 1K?
No.
Yes or no? No, right? So what is done is when you're taking these measurements, there is a filter that is added to the sound before it is calculated for SPL, or rather when the calculation is happening, when your software or your SPL meter is doing the computation, it adds a filter to it. Okay, so it starts negating frequencies above and below the frequency range depending upon the curve you're using to give us more meaningful readings. So you might have seen in certain equipment, right? Whatever dB SPL, and then you'll have a parentheses. In the parentheses, you'll have a written there. That means it is dB SPL A weighted. In most cases, we use A weighted scales only. Okay? I have an SPL meter here. I'll show you how that thing is done in just a bit. Then we have a C weighted scale. You notice now how the C weighted is more flat in the mid frequencies and takes more of the low frequencies into consideration. Where do we use this? Very important in live sound. Okay. Now next, come on, change. This is the Fletcher-Munson curve, and if you see, there are these dotted lines. Forget the yellow dotted line. Look at this blue dotted line here, and the green dotted line. The blue dotted line is basically the A weight scale. Okay, it kind of corresponds to what we human beings listen to at about 80-85 dB SPL. Okay, what is our curve like? And as we go, and as the sound gets louder and louder, what happens is our hearing also flattens out, and that is what the C weighted scale moreover relates to. So especially when you're doing live sound where we are playing our system at about 100 dB SPL approximately for 2.5 hours, and an average, not always at 100 SPL, but it's an average. So we are more worried about the C weighted scale, because if we don't look at the C weighted scale properly, we are not taking, if we are only looking at A weighted scale at 100 dB SPL, it's not a right representation. Okay? So of course, in a live sound scenario, mostly system engineers, what they do is they'll have a weighted scale in front of them, and they'll have a C weighted scale in front of them, and they'll kind of, reference both of them, because when you're playing music is not playing at one level, it is dynamic in nature. Okay? So to give them proper readings, they mostly will have two kind of scales in front of them. So for the louder parts, they'll look at the C weighted scale, how the system is, whether you're having even coverage from the front to the back, left to the right, top to down or no. Are you getting it?
Yes, sir.
Okay, so why these are nothing but filters that are added to the measurement itself. So your audio is captured by the microphone and it is sent for processing. When the processing is happening, these filters are added. And that's why these softwares can give you two different readings by taking just one audio wave in. Okay, taking just one impulse in. Through one microphone, it will take whatever the audio signal is coming and process it in two different ways. One for A weighted and one for C weighted. Okay, if I'm just going to make this whole graph a little bigger, and you should be able to see a little more clearly. The yellow dotted line is a B weighted curve, which we are not going to, it's out of the scope of what we're going to talk about today. Any doubts so far? Okay, so if Atharva can just spotlight my camera only. Or actually, use this guy, yeah, spotlight this guy. I'm going to play some noise on the speakers, okay? And I'm going to show you this SPL meter that's in my hand, and I'm going to do an A weighted reading and a C weighted reading. and we see how it is different. You will notice that the C weighted is slightly gets a little more louder compared to, in the sense that it gets a little more louder, not on the speakers. The speakers are not going to get louder. They're going to remain at what level they are playing. Only the reading will get maybe a couple of dB higher compared to what the A weighted scale is, because C weighted takes in more information in the low frequencies. Okay? Yeah. Cool. I'm going to switch my microphone off and play some noise. Channel number 1. Did anyone register what level were we at? So even if I'm speaking, right? Hold on, quick. Start video here. So even if I'm speaking, can you see this? Can you see the level changing?
Yes,
Okay.
sir.
So now this is basically A weighted. Okay, so I'm just going to again play some noise and just see what level I'm trying to. I'll see if I can put a peak hold here. Hold on.
So were you asking for the last level?
Yeah, for the last level. Did
We were at
anyone register?
88.5.
How much?
88.5.
88.5. Okay, so that was A weighted. Now I'm going to put it to C weighted. There's a button here, okay, which says A and C. So right now it's on A weighted. I'm going to press it and put it to that is C weighted right now. And now we're going to play the noise at the same level. See if you get a change in the reading. You got the difference, right? About a 4-5 dB change is there, right? Here we were at about 90. So I did not hold it at the exact same position, but you should get the idea. You'll always get anywhere from a 2 dB to a 4 dB difference from a A weighted scale, because C weighted is taking more data in compared to your A weighted scale. Is that clear?
Yes, sir.
Hold on, let me get to the screen share again. So in most cases, you would just need an A weighted reading. You don't need a C weighted, because like for a studio, if you're working in a studio or something, in most cases you're not going to be playing audio at about like 100 dB SPL all the time, right? You're going to be playing audio at say about at the most 85 to 87 dB SPL. Correct? You're not going to be cranking sound out that much. But in a live scenario, you're almost at an average of 98 to 100 almost all the time. Okay? There is another thing in average, something known as LEQ. Okay? Because in audio, because we are on a logarithmic scale, we cannot directly calculate average. Okay, so it's basically there is the whole averaging is done. There's another algorithm that takes care of all the averaging. So you in your software now, we are working on a SPL meter which does not have that capacity. But if you're working on a proper software, you can set how much time you want to measure for. So say you want to take readings and average readings for every 10 minutes or every half an hour, you can do that. So the software will measure for half an hour, and every half an hour it will keep refreshing the readings. Because our hearing is more of an average hearing. We do not respond to peaks as well as we respond to an average level. Does it make sense? Okay, so
Yes,
the thing
sir.
is, measuring audio is not very, very simple. It's a very, very complex task, and you have to know exactly whether or not you're taking right readings. And that's the reason why, as we progress in this class, you'll get to know, there are certain steps you need to take to make sure that you get proper readings. So what we are doing today is an introduction. It's not the full-fledged thing, because this whole field is a study by itself to how to take proper readings in audio. Okay, so far we have just seen why are we doing this stuff? Why are we doing this whole exercise? Because our hearing is not linear, it is non-linear. Okay? We have to understand, if you're doing audio measurements for studios or for live, whatever, you have to understand how human beings perceive audio in the first place. Okay? Any doubts here? Are we good? So that gets me to the next part. What is a 2-channel FFT measurement? Anyone heard of this term before? For those of you guys who've probably done science or engineering, might have come across this term before. FFT. Does it sound familiar? Yes, no? Okay,
No,
anyway,
sir.
so FFT is basically nothing but something known as fast Fourier transforms, okay? Now, what is a fast Fourier transform? Is basically, it is an algorithm that takes in complex data and breaks that complex data into its building blocks. For example, I played some noise, okay? If I put this noise into an FFT, it will basically break that noise up and it will tell me what different frequencies are playing. Not only different frequencies, it will also tell me at what time what thing is playing. Now, what is time domain, what is frequency domain, I'll just come to that in a bit. But FFT, all of us have seen it at some point or the other. As I said earlier, you might have opened Ableton, you might have opened Logic, opened the EQs there, and open this analyzer there, right? You have a wiggly line, and then you can get to know, okay, certain frequencies, if they are more than what you need or less than what you require, you can do changes and change that curve. That is an FFT. That's a single channel FFT. Okay? You can see on the x-axis, you can see frequency. On the y-axis, you can see the amplitude. Okay? And you can, so what that software has done is taken the complex wave of your music and has broken it up into its independent frequencies. And you can see it on your screen. So that is what an FFT does. It's as simple as that. It's very simple to probably understand, but it's a very complex algorithm that is now put into our computers. Okay, this is something that someone had made on pen and paper almost like 100 years back. Okay, and it is this same algorithm is used for a number of things, not only for audio. Okay, you can use the same formula for light, for population growth, for a lot of things. Okay, it's basically something to do with calculus and stuff. So let's not get into that. But it is nothing but it's an algorithm to take in complex data, break that complex data into its building blocks. Any doubts here? Did you understand what an FFT does? Fast Fourier transform. We are not going to get into the formula part of it because we are going to understand how to use the application and not how to build an application. Everyone on the same page?
Yes, sir.
Okay. So what you see in front of you is something known as a frequency domain signal. Now these two things you'll have to keep in mind because using FFTs we can do multiple types of measurements. Okay. So we can get really complex with it, but we're just going to understand the very, very simple basics of it. Okay. So we have on the y-axis, we have amplitude. Amplitude is going to remain there always. Okay. That means how loud a particular, not how loud, but what is the level of that particular signal. Okay, depending upon where you're measuring it. On the x-axis is frequency. So now that's why it's called frequency domain signal. Means we are measuring frequency against amplitude. Is that clear? So now you can see, right? You can see a curve there, and then you can see different peaks here and some nulls there, whatever. And you can pick out what frequency it is. Okay, like for example here, it is somewhere around 500 hertz, and at what level it is, you can pick out. It's about -80. Okay, now -80 what we don't know, but you can get an approximate understanding of it. Right? Does this make sense? You all have all seen it at some point inside your DAWs probably. Yes or no?
Yes, sir.
Yeah. Next is something known as time domain signal. Now, this is something that you might have never seen before. Okay. Now, what is time domain signal and what is frequency domain signal? How do we get to know whether a signal is time domain or frequency domain? By seeing what is there on the x-axis. If x-axis has frequency, means it's a frequency domain signal. If x-axis has time, means it's a time domain signal. Now, what you see on your screen is an impulse response. Okay, to give you an idea of how it looks. Okay, we'll come to Channel FFT in just a bit. Hold on. So I'll tell you how this looks in a three-dimensional world in just a bit, but we'll just understand what is two-channel FFT, and then we'll do a couple of things together. Okay, so when you see frequency on the x-axis, it's a frequency domain signal. When you see time on the x-axis, it's a time domain signal. Okay, keep these two things in mind. Do you understand? Any doubts here? Now, why do we need all that information? We'll come to that in just a second. We spoke about single channel FFT, where you have x-axis per frequency, y-axis per time, and then you play some music in your software, and then you put one analyzer on that channel on your master fader, or maybe on your whatever channel fader, and then you can see that line move, and then you do some EQ, and then you can see the curve change. That is a single channel measurement. Okay, what is a dual channel measurement? What is two channel measurement? A two channel measurement is basically when you are comparing one data against something else. Okay, and that's what all your software like Smart and Systune do. They compare what is coming out of the speakers to what is actually been played through the speakers. Okay, so let me explain that to you. So in front of me right now, I have a measurement microphone. I'll cut to the camera in a bit, but just understand, I have a measurement microphone. Okay, this measurement microphone is omnidirectional in nature. Okay, it's flat frequency it's flat in frequencies from 20 hertz to 20 kilohertz at least. It has a pretty much a flat frequency response. Above and below 20 kilohertz, it might change depending upon which manufacturer you're working with. For the most part of it, any omnidirectional measurement microphone should work. It has to be a measurement microphone, okay? It cannot be a normal omnidirectional microphone that you would use for vocals and stuff like that. Don't change, I'll move to it in a bit, okay? So this microphone is peculiar because it has a flat frequency response, okay? Secondly, you need at least a two-channel audio interface with two inputs and two outputs at least, okay? Third thing is you'll require any laptop. Does not need to be a super powerful computer. It can be any computer. Fourth, you'll need some sort of a software to do the measurement. Okay, you have softwares like Smart, you have AFMG Systune, you have Open Sound Meter. Today we'll be using Open Sound Meter. Open Sound Meter is basically a freeware that is available. So any one of us, or you guys can download that and at least start taking some readings. Even if you don't have a measurement microphone, it's fine. You can practice taking readings. You don't always require a measurement microphone, but to take very clean and good readings, you'll require a measurement microphone. To start practicing, you won't. Okay? So now I'm going to explain to you how this whole two-channel thing works. Okay? If you want to do SPL, you will require an SPL calibrator, because your microphone or your sound card or the software does not know what SPL it is playing. You have to give it a reference. So the SPL calibrator is small cylindrical, kind of things which have a speaker inbuilt on them, and they are airtight. So they have only one opening. The moment you put the measurement microphone inside that, it creates an airtight seal, and then you can play a tone at 94 dB SPL or 114 or 110 dB SPL, depending upon the brand you're working with. Set up the gain, optimal gain, and then run a whole SPL calibration within your software. Open Sound Meter cannot do it, but Systune and Smart can do it. We are not going to get into that because I don't have an SPL calibrator today. But you could also use such kind of things. This is only an SPL, handheld SPL meter, but most of these guys don't have, they're not very, very precise. When you're running with a software like Systune or Smart, they're much more precise than a simple SPL meter. Okay? Let's go to the connections. Now, I have a computer, okay? I have an interface with the computer. Then I take my measurement microphone and I connect it to one of the inputs. In this case, I've taken the measurement microphone and I've connected it to channel number 1 of my interface, okay? don't bother about mono, stereo, forget all of this stuff now, because we are not dealing with music, we're dealing with just measurements, okay? So some of you might get confused, hey, we have two, so we need two microphones and this and that. No. We can work with one microphone, and we need the next input for a reference signal, okay? Now, these softwares have a tone generator built into them, okay? So we have to make sure the tone generator comes out from the computer, plays on our speakers, and another copy of the tone generator has to go back into the software. It's called a loopback, okay? So we take two copies out of the interface. One copy goes to our speakers. The other copy goes back into the interface on the second channel, so that the comparison can be done. Are you understanding or confused?
Yes, sir.
Yes, sir.
We are doing a two-channel measurement, okay? Means what I am trying to do, I'm trying to, first of all, I'm playing some noise, okay? So that noise is coming out of my speakers. It is getting picked up by my measurement microphone, okay? Now that measurement microphone is sending that data to the software on the computer. But we need a clean signal to compare it against, right? Like let us go to the example of buying those tomatoes. If you go to the vendor and say, you know, I want 1 kg tomato, he's just going to pick it randomly and give it to you? No, he's going to take few tomatoes, put it in a weighing scale, right? He's going to put a 1 kg weight on one side and then take few tomatoes and compare how many tomatoes he needs to put in that empty bowl, compare it to a 1 kg weight. Does it make sense? That's exactly what we are doing here. We are taking an output from the computer and running it back inside the computer. Okay, that is a reference signal. Then whatever is coming out of the speakers goes through the microphone and then gets into the computer. So now the computer has two signals to compare it. We specify channel number 2 is our reference signal and channel number 1 is the signal that is to be measured. Does it make sense? Anyone has a doubt? Doubt hai to pooch lo. I'll just sip some water. Yeah. No, you can't use the software loopback because what has to be taken care of is also the what has to be taken care of is also the time that is taken to process the data within sound card, right? Because the D2 and A to D conversion will require some time. So that also needs to be taken care of. Hence, hold on, I'm just lost right now. You guys are seeing my screen, right? Yes, exactly.
Yes, sir.
I have lost the PPT screen. Where's it gone? Hold on. PPT kahan gaya? Keynote there. Okay, so let's go back. So basically, the software loopback would not work because your sound card is going to take some time to process the data to convert the data to analog. So from analog to digital and digital to analog. So that time taken for that also needs to be taken to consideration. Okay, if you do a direct loopback internally, right, that time is not going to match. So then you won't have a right reference. I hope that answers your question for whoever who asked the question. Okay, so you cannot use a software loopback. You will have to use a hardware loopback. Okay, you have to have at least one loopback signal. Then you can have multiple microphones. You can have 16, 20, as many as you like, depending upon how many readings you want to do. Okay, so microphone gets connected to our input number 1. In this case, this is exactly how it's happening in this room as well. And the outputs from your sound card, one is going to your speakers. That in this case, it is going to my console, and the other one is getting looped back into my M4. Any doubts here?
What are we trying to measure?
We had anything. It could be phase. It could be impulse response. It could be a number of things. It could be simple RTA as well. So we are just setting up the system to do 2 channels of measurement. I mean, to do a measurement and a reference. Okay, to do the measurement, we need a reference. That's the reason why we have a loop back and we have one measurement microphone. Okay, so once this setup is done, we can measure phase relationship between different sources. We can measure the RTA of the room, do RT60 measurements, a lot of things like that. Because now the computer knows what the pink noise it is sending sounds like. It knows the timing of it. Then the output coming out of the speakers is measured by the measurement, it's taken in by the measurement microphone and sent for processing again. So then it will compare what it will start comparing. Okay, what have I sent and what am I receiving back again? Does that make sense?
Yes, sir.
So could you
Anyone
repeat that?
confused here?
Could you repeat that?
So, like for example, I'll give you that example again. If you go to buy, say, tomatoes, okay, I tell you go and get me 1 kg of tomatoes. You go to the vendor, you tell him, you know, give me 1 kg of tomatoes. What the guy does he pick some random number and give it to you? No, right? He'll take a weighing scale, he'll put 1 kg weight on one side, then he'll take some tomatoes and put tomatoes till the time both the weights balance out. Right? Yes or no?
Yeah.
Assuming all of you all have had that experience at some point in life. If you all haven't, then you know you need to go and get a life. So anyway, so this is the same thing we are doing here. Okay, what we are doing is we are having a reference signal that the software is sending out. That reference signal, it is pink noise, is coming out of the computer. That signal is split into two parts. One is going into the speakers. The other is being looped back into the computer. So now when the microphone is picking up what signal is coming out of the speaker, that signal is compared to what the software is sending in the first place. And that's how you get to know what is the difference. A simple difference could be RTA. I'll show you an example. We'll run the software and show you an example. But I hope you understand the concept of the connection. Because this is the most basic thing you need to understand. If you don't get this right, it is very simple to do, but if you don't get it right, you will not get proper readings. You will not know what to compare and how to read the whole thing. Is it clear, or do you want me to explain the whole thing all over again? We can do that. I'm in fact going to move the camera and show you the connections also. Should we go ahead, or you want me to repeat it all over again?
So when taking multiple measurements, either with a one microphone setup or a multiple microphone setup, all of those measurements are relative to each other, or are they relative to the loopback?
They are all compared to that loopback.
Okay, but
okay,
so the placement has to remain in the same place.
Sorry?
The placement would have to be in the same place then. Any discrepancies?
That's a different story. That's the next part of it. Forget the placements, you know, because we have not yet decided what we are going to measure.
Okay.
Okay, so the placements is a different topic. We'll come to that in just a bit. But now you just understand the concept of the loopback and why are we using the measurement microphone.
Yeah.
Okay, the measurement microphone is basically taking whatever signal is coming out of the speakers. Once the signal leaves the speakers, a room will get involved into it. You know, any obstacle will get involved into it. The speakers themselves are going to change the signal in a certain way. The console is changing the signal in a certain way. The cables are changing the signal in a certain way. So all those changes are compared. You know, what are the changes that are happening against what has been sent out. Okay. Now it depends upon what exactly, in this case, I want to measure what is coming out of the speaker, means all those changes that are happening from the console, through the cable, through the amplifier, through the speakers themselves, all of them show itself as a combined output. We cannot make out what different changes are happening in the console versus the speakers. We can do that if you want to measure, we can do that as well. But that is a slightly different connection. For now, if you understand this, we can do different kind of connections to do different kind of comparisons. Okay, if you know this, right, you can compare one preamp from another preamp. You can compare one console to another console. You can compare a lot of things, and you can actually see the difference between what each mic or each console is doing. If you know what this concept is of doing the connections, it's a very simple connection. It takes 2 minutes to do it, but just you need to understand how to put the right things in the right place and also choose the right options in the software you're using. Is that clear? Okay, so I'm going to quickly switch cameras, and I'm just going to show you what connections we have done in this room. Okay, it's the same thing what we have done on the screen. I'm just going to show you physically how they're done. Okay, I'm going to stop my screen share. Done. Just a second. Cool. So first of all, I have my computer that is running open sound meter, okay? What this interface does and I just want a reference. I'm running open sound meter, okay? So that is connected to my audio interface. The audio interface is a Motu M4 in this case. It has 2 mic inputs and 2 line inputs. I'm using all of them right now. I'll tell you why I'm using what in just a bit. Okay, these 2 are connected by USB, the interface and the computer. Then I have a console which is basically the heart of this entire system. All the audio that is getting in and out is going through the console. Okay. Now, coming to the other side of things, I have a measurement microphone. This is the Behringer ECM 8000. It's not a very expensive measurement microphone. It costs about 4,500 bucks. Okay. This is connected directly to the sound card. Am I stuck or is it working? Are you guys seeing me in real time or am I stuck on screen?
It's very laggy.
It's very laggy. Okay, I'm just going to go very slow with it. But you should. So the measurement microphone is here. Okay. Then that measurement microphone is connected directly to the interface, to channel number 1 on the interface. What happened?
So the iPad is moving very quick. So if you could use that.
I'll use the iPad. I'll use the iPad. Hold on. Just spotlight the iPad. Don't just use it. It's okay. Just pick the iPad only. You can swap the cameras so that data. Yeah. Okay. I'll go through it again. Computer. Okay. To interface. These 2 are connected by USB. Okay. I'm running the software called Open Sound Meter. Okay. Then I have the console, which is the heart of the system. I have a measurement microphone here, not the Neumann. The Neumann is what you guys will be listening to. There's a measurement microphone. This is the Behringer ECM 8000. It's about 4,000, I think 5,000 bucks. Not very expensive. This is connected straight to the channel number 1 of my interface. Okay, it's going in here on channel number 1. Understood so far?
Yes, sir.
Yes.
Cool. So now, open sound meter is giving an output. The output of open sound meter is going from output number 1. Okay, so output number 1 right here, left output, is getting connected to, hold on, let me just check everything properly. Yeah, so this is output number 1. This is output number 1. These are 3 and 4 inputs. So don't bother, don't look at this. This is here, this red cable is output number 1. Okay, the output number 1 is getting connected to channel number 1 of the console. Input number 1 of the console. Okay, so this is the output that is going to be playing on the speakers. With me so far?
Yes, sir.
Okay. Now for the loopback, I have this cable, this green cable is output number 2. Okay. This cable is going all the way back, getting looped back to input number 2 on the interface. Make sense? This one. Let's come ahead, come this way. Okay, this is input number 2. That is coming from output number 2. Understood so far?
Yes.
Okay, so now open sound meter is sending the output. That output is coming from channel number 1 and channel number 2. Channel number 1 is going to the console. The console is sending it to the speakers. Channel number 2 output is coming back into the interface and going back into open sound meter. So that open sound meter knows what it is sending. So open sound meter will calculate the delay time and a lot of things that is this thing. So it will tell us even how much delay time is happening internally also. Is that clear?
Yes,
Anyone
yes,
needs
sir.
explanation all over again? So now when I play some sound, this is channel number 1 and that is going to my speakers. Okay? Itna clear hai?
Yes, sir.
Yes, sir.
Okay, so this is how you will connect all, it doesn't matter what software you're using, all the softwares have the same connection, absolutely same connection. So you don't, once you understand this, I'll also take you to the run you through the software and figure out a couple of things, and we'll then check out a couple of things within the software. You understood the whole loopback thing because that's the most, what do you call it? The most crucial thing to understand. Should we go ahead?
Yes, sir.
Okay,
Yes.
so I'm going to go switch back to the PPT and zoom. Super. You can keep that on. Okay, connection. This is something that you have to really understand, because if you don't understand this, nothing will make sense to you. Okay, so as I said earlier, we can do two kinds of measurements. We can do frequency domain measurements. We can do time domain measurements as well. Now, time domain measurements is something known as an impulse response. Okay, that is not an impulse response is nothing but an inverse of the FFT. Okay, basically, if some of you are kind of familiar with calculus, it's basically, you can say the FFT works on a derivative by differentiating it, and the inverse of it would be integrating the entire thing. So, yes. Yeah, reference signal is coming out of channel number 2 and going back into channel number 2 input. Channel number 2 output से आके channel number 2 के input में जा रहा है. वो है reference signal. The measurement signal is the one that has been captured by the microphone, which is going into channel number 1 of the interface. Does that answer your question? Is that clear? Anyone wants me to repeat the whole thing again? We can do it. If not, we'll just go to impulse response. Now, what is the whole thing of impulse response? Now, you see this is basically a 3-dimensional representation of the entire thing. So you can have amplitude on the y-axis, you have frequency on the x-axis, and now you have time on the z-axis. So now when we are looking at an RTA where we have frequency on the x-axis and amplitude on the y-axis, we are looking at one side of the signal. We are not looking at the entire, we are looking at one dimension only. Okay, so at 2 dimensions only, that is frequency and amplitude. If you want to look at the impulse response, we just need to turn this whole thing. So instead of looking at the x-axis, now we'll be getting time on the x-axis. So what happens here is now we have amplitude, we have frequency on the z-axis, and we'll have time on the x-axis. Okay, and my PPT is gone for a toss, but anyway, I hope you get the idea. So we're just changing our perspective of looking at the data. Do you get it? Understood or confused? Anyone? Confusions? So instead of looking at the time on the x-axis, instead of looking at the frequency on the x-axis, we are just turning that whole Cartesian coordinate around, and we are looking at the time on the x-axis instead of the frequency. So the frequency has moved to the z-axis and the time has come to the x-axis. We're just kind of flipping it around. Is that clear?
Yes, sir.
Yes, sir.
Difference between time, it's the same data. It is just, imagine it's the same, exact same data, but you're just looking at it from 2 different points. How many of you all have seen that waterfall, representation? If you all have used a software like our, Room EQ Wizard, or even if you have opened Serum and stuff like that, you have seen that little water wave things that comes, right? If you are people who use synthesizers and stuff, I think Serum has that, if I'm not mistaken.
The wave tables.
Yes, those wave tables. Okay, it is nothing but that's the thing. It's one dimension is time, the other dimension is amplitude, and one dimension is frequency. It just depends upon which perspective are you taking to look at it. Okay, so when we are looking at an RTA, we're changing a perspective where we get time, where we get frequency on the x-axis, and when looking at impulse response, that is when we want to do a comparison between time arrival times of different sources. That's what we use impulse response for. We're getting the time on the x-axis. Okay, where do we use impulse response? We use it to measure RT60. We use it to do time alignment of speakers. That's where we use impulse responses in an FFT, in the whole FFT domain thing. Okay? Any doubts? Yeah. Question is there, apparently. Huh. Yes. IFT would be a representative of amplitude and time. Okay? And basically, when you see an RTA, that is an example of frequency versus amplitude. You just read what's there on the x-axis. That's it. It'll tell you. Clear? Some reverbs and also have it. They'll have this. I think this new. If you go for this, I don't know. I think when it comes to Yamaha live consoles and all, they have that little representation. Okay. It's all about data. We are not right now. We have not come to the point where we're measuring the room. It's all about how to understand this data and what this data is trying to tell us. See, if you're looking at a screen, if you don't understand what is there on screen, how to read that data, there's no point of using the entire software only. Okay, so right now we're just trying to understand how to read this thing and what these different things mean on the screen. Is that clear? Any doubts? Now we come to a very complicated thing, which is not actually complicated. It's pretty simple, but we'll look at a PPT and then we'll also listen to some stuff and see if we can make out differences. Okay, phase. We all have studied about what phase is.
Yes, sir.
Have we or haven't we? Okay. So what is phase? Basically, relationship between two waves with respect to time. Right?
Yes, sir.
Yes.
Do you all understand the definition? Okay, anyway. So let's look at the simple thing what you might have learned in class. Okay, you take two signals of the same amplitude and the same frequency, and then you sum them up together. You would get a increase in amplitude, right? What happens when you do the opposite? When you polarity, this is called polarity inverted. Okay, where the peaks are opposing each other. One peak is positive, the other peak is negative, and they are at the same time. They're playing at the same time. What you get is you get no signal. Okay. Last thing, which is what happens in the real world, is something known as comb filtering, where we have two waves that are playing at different times, but they have the same frequency. So you have a time difference between them. Okay, the x-axis being time right now. So this is a time domain signal. Right? Y-axis is amplitude, x-axis is time. So now you have summation in one part, you have cancellation in another part. Okay, then you have again summation, and then you have cancellation, then you have summation again. Okay, the resultant wave is what you see on screen. Looks and sounds familiar? Yes?
Yes, sir.
This is called comb filtering.
Yes.
And this happens everywhere. Okay? So once you've learned about comb filtering, this is a time domain signal. Okay? Let us understand how to read the phase trace. Now what you see might look like wiggly lines on a screen. We need to understand how to read that phase trace now. Okay? So let's first understand what is to understand how to read those phase traces, we need to understand what's the phase wheel in the first place. Okay? So we have 0 degree, 90 degree. We all know the Cartesian, not Cartesian coordinates, but we all know the degrees of a circle, right? We measure the radius of a circle in degrees. So we know what is 0 degree. The starting point will be 0 degree. Then we have 90, 180, and 270. Simple, everyone understands. This is how it relates to an audio wave. Okay, if you open up, basically if you break one part of the circle and open it up, it will turn out to be that. So that blue line that you see in the center is your 0 line. And if we compare from there, we start comparing, we can go to 0 degree, 90 degree, 270 degree, 180 degree. And then when the cycle repeats again, it's not 360, but it has moved ahead in time. It starts from 0 degrees again. Okay, because the x-axis is time. Samajh hai? Are you all on the same boat right now? Or
Yes, sir.
Okay, so let's take this one step further. Okay, let's look at this as a cylinder instead of now just a two-dimensional circle. Okay, so we'll have 0 degree, 90 degree, 270 degree, 180 degree. Make sense? Yes or no?
Yes, sir. Yes.
Now imagine if we take a scissor and we cut from 180 degrees. Because it's difficult for us to read into, our screen is 2-dimensional, right? We need to see things in 2-dimensional. Papers are 2-dimensional. We need to see things in 2 dimensions, but this is 3D. So how do we make it into 2D? We have imagine that we take a scissor and we cut that cylinder that is formed, we cut it from 180 degrees. So what happens? And we open it up. What happens is you see a 2-dimensional thing where you have 0 degree in the center. It's again too long to open. You have your 90 degrees there. You have 270 below that. You'll have 180 on top. And then you'll have 270 and minus 180 as well. Make sense? Did you understand this? Is there a piece of paper here? हाँ. ज़्यादा flimsy हो गया ये, but ठीक है. Should work it out. Are you getting it? Anyone has doubts? Okay, this is probably work. Just this thing, my screen. Come on. I don't have a piece of paper. I should have got a piece of paper earlier. But imagine this is what we are looking at. Okay. Just take this up. Okay. Imagine this is what we are looking at. Okay. 360 degree of a circle. We cut it open from here and we open this up. Okay. So you'll have 0 degrees in the center. You'll have plus 180, minus 180. 90 degree will be somewhere here and 270 degrees will be somewhere here. Does that make sense when you open up it into
Yes, sir.
2 dimensions? Now,
Yes, sir.
why are we doing this? It will make sense to you in just a bit. Yeah. Yes, absolutely. So you're getting it, right? Let me get back to Zoom and share my screen again. Okay, so makes sense. So basically I'm opening the cylinder and we're making it in 2 dimensions. Okay, so now when my reference signal and measurement signal are absolutely in phase, you're going to see nothing on screen. It's going to be on flat line. You're not going to see that line. It's just going to be a flat line. But the moment the measurement signal starts getting delayed, there's going to be a trace that is created and this trace will start pointing downwards. So when the trace is pointing downwards means that incoming signal, the measured signal is getting delayed by that many degrees and you'll be able to read that delay. Okay? And the next thing is when the trace is moving upwards, it means that the signal is actually arriving earlier. Now, how can a signal arrive early? It's not a time machine, but when it's arriving earlier compared to the reference signal. So if you have moved, if there's a problem in the delay and you have moved it too further away, certain frequencies can actually start arriving earlier, especially if you have speakers which have multiple drivers in them, okay, and they have some distance between the drivers, and you're trying to align them to a sub. You might move that entire speaker behind virtually by giving it a time delay, not your delay effect. I'm talking about actual time delay. You're delaying that signal getting out of the console itself. You might pull that behind, but at a certain point you might feel, okay, the high frequencies are coming in earlier compared to the reference signal. Okay, that could happen. But what you need to keep in mind is when the trace is pointing downwards means the signal is getting delayed. When the trace is pointing upward means the signal is coming earlier compared to the reference signal. Does that make sense? Yes or no?
Yes.
So this is right now the end of the PPT. What we are going to do is we're going to listen to some things and I'm going to share my the open sound meter screen for you. Okay? Any doubts that you want me to clear before we get into the listening and the looking at the software part of it? Anything you want me to repeat again? Are we good all? Yeah. Hundred SPL A weighted sound will generally, yeah, will basically be, the reading will be slightly softer. I mean, you'll get a lower SPL value on your meter, okay? Because the A weighted filter is not going to compute that 100 SPL, the 100 hertz as much. It is going to try to negate it depending upon the slope rate. Okay, but a C weighted will seem that the 100 dB will, the 100 hertz will seem louder on the C weighted reading. Okay. So if you take 100 SPL, if you play a 100 hertz wave, right, and you take and measure it and put that measurement in A weighted, you'll feel it is soft. The moment you switch it to C weighted, it will feel it is more. So if you're doing a measurement of 100 hertz, 50 hertz, 40 hertz, you will put your meter into, your SPL meter into a C weighted scale, C weighted reading, and then you'll take that reading. Okay. But see, it all depends upon what are you reading, what are you measuring for. Okay, if you're measuring for a studio, in most cases in the studio, you'll be listening to at 85 to 87 dB SPL is the comfort zone where most of the people listen to the monitors at. So there it doesn't make sense to use a C-weighted reading, right? Because you're not going to play the audio for a long time. Maybe you might play the song for maybe 30 seconds, you'll pump up the volume and listen to one chorus or one verse, and then you'll come back to where you are mixing, right? You're not pumping your level out of the studio at 100, 103 dB SPL always, because if you do that, you're going to lose hearing within the next year and a half. Okay? Does that answer your question? So it doesn't matter which frequency you're measuring, what matters is where are you measuring it? What is the reason for you to measure it? That's what you need to understand. So if you're measuring in live sound, you will measure A-weighted and C-weighted. Because when you measure only A-weighted, it is not taking the sound waves that are coming out from the subwoofer, is not calculating them properly. So to measure that, you need to move into C-weighted. Okay? So that comes only with more experience and practice, like to understand where exactly you're measuring. What is the reason? So you need to ask yourself, what do I need? What am I trying to understand by taking this reading? That's the first thing you need to ask yourself. Then you take the reading.
So where would you measure from?
Good question. So again, it depends. See, if you're in a studio, simple. You're measuring from the sweet spot.
Yeah,
Okay.
but in live situation?
In live sound, that's the thing. In live sound, you're taking an average measurement. You're measuring from different locations. That in that time, you won't have one measurement microphone. That's the reason why I said you can put multiple measurement microphones. You'll put multiple measurement microphones in multiple locations, and you will average that out. And you will see, especially if you're working, say, for example, in a stadium, you'll probably put one microphone right in front of the stage where you feel the first row of the audiences. One microphone you'll put maybe at the console. You'll put another microphone in the stands, on the third level of the stands, and see what is the level you're getting there, what is the SPL level you're getting there. You'll compare it with the frequency response, because the SPL does not SPL measurement will not understand whether it's the sound coming directly from the speakers or it's a resonance of that stand that you're putting the microphone on. So you need to compare that with the frequency data. Okay, so to do an SPL,
and that's what the tone generator is for then.
No, tone generator is just giving you a signal output. The tone generator, you're not using an external tone generator.
No, the loopback is to compare it, right?
Loopback is not to compare SPL.
Oh, okay.
It is for time domain signals and for frequency domain signals. SPL, you will basically do a whole SPL calibration will be done. Unfortunately, Open Sound Meter does not have it. You need two extra things for it. You need a proper FFT which has the SPL calibration tool in it, and you'll also need the SPL calibrator, which is you're supposed to push a microphone in the SPL calibrator, turn on the SPL calibrator, then turn up the right gain, and then set up that calibration inside Smart or System. And so the moment System or Smart gets to know, okay, fine, they know what 94 dB SPL is or what 110 dB SPL is, and then it'll do a SPL measurement over that, comparing it to that gain setting that you have given.
So two more questions, if you don't mind.
Yeah, go ahead.
So the first question is, okay, I'll ask the second question because I can't form the first question.
Yeah.
Wouldn't these values change when people enter the stadium?
Of course they will.
So how do you work around that?
So see, the thing is, it is a what do you call it? It's a control compromise, you can say. Okay, so you need to know at what level your you're aiming at. For most places, at least in the West, now they have a upper limit. They have an upper limit of about 103 or 100 dB SPL over the entire show. Okay, so when you are measuring without the people, you are giving that little headroom. You're giving a headroom of 2 or 3 dB. So you might get, and the best thing is nowadays, if you're putting up a line array system, you can actually create that entire venue inside your software. It can do all the, assumptions within the software. It will basically simulate audience being there. It will do all the simulations for you. So you don't need to. So if you're running, if you know to use your, now when I talk about software, it's not the FFT software. Say for example, if you go and buy like an Acoustics, which has a software which is called Sound Vision. Okay, in Sound Vision, you'll put the entire dimensions of the room. You'll put the dimensions, or you'll put how many speakers you're working. It'll give you display angles. It'll give you then you can do a target trace. You can figure out what SPL you want, and it'll tell you at what level to keep the amplifiers. All of the data will be given. You can use softwares like Ease Focus, and there's another software called Ease, which is a simulation software which a lot of acousticians use to simulate what is happening inside a room. Okay.
I assume, are these proprietary softwares or?
Proprietary softwares.
Okay.
Like Ease Focus is made by AFMG, which is free of cost. Okay, it is. The problem with Ease Focus is that it does not take into consideration walls and ceilings. So you won't get a very accurate SPL measurement, or you won't get reflections of a wall, but it does the job to a great extent. If you go and buy Ease, which is extremely expensive, on that you can actually, simulate a room in a very, very advanced way. You can actually play pink noise. You can place a probe, a microphone, a virtual microphone inside the room, and you can listen through it, how it will sound inside your headphones also. You can change the materials of the wall, of the ceiling, or the floor, and you can hear the changes in real time, all as a simulation. So,
and I assume these topics go further further than what we are talking about today.
Yeah. What we are talking about is just literally like measurements 101.
Right. And the other question was, are these values recorded or measured by the venues beforehand, or is it done at setup?
No. You have to do it. If you're a system engineer, you do it by yourself. If you're setting up for studios or you're setting up for an auditorium, you take in your rig and you go and take the readings by yourself, and you can store those readings within your software.
But again, won't it change with the different venue?
Yeah, but if you're installing, it changes. So you do the speaker, everything is planned in advance, right? You don't go on the day in the morning and listen. Everything is planned in advance.
Yeah.
If you're setting up for a stadium, you're doing a show in D.Y. Patil Stadium, you'll ask for the blueprint of D.Y. Patil Stadium, take all those measurements, dump them in your software, whichever PS system you're using, and you'll start building it 2 or 3 days in advance. Figure out where you're going to rig your speaker system stuff up. If nowadays, if you're setting up studios or setting up venues like auditoriums and all, the blueprints are sent to the acoustician even before the place has been built. Then that guy will put all of the stuff into Ease and start deciding what goes where. This is done even before the building is built. Then they'll basically, once the building is built, depending upon what data they have got. So because in a blueprint, they'll have all the dimensions. You'll have how high the ceiling is, how wide the walls are, whether it's a circular room, it's a rectangular room, or whatever it is. Then they'll decide, okay, what kind of soundproofing needs to be done. Soundproofing is different, acoustic treatment is different. So what we are dealing with is acoustical measurement. We're not bothered about the soundproofing part of it. Okay, so then once you have understood what is going to be the surface in the room, you put that in your Ease, you simulate, and after you figure out what you figure out, okay, where do I need to put my bass traps? Where do I need to put what kind of what kind of bass traps do I need to put? Do I need to put on the corners, or do I need to put on the ceiling corners, or do I need to put diffusers? All that stuff you then decide depending upon what data you're getting. There is a software called Room EQ Wizard also. Open Sound Meter is a real-time software. Room EQ Wizard is not a real-time software, but it can do everything what an Open Sound Meter does, and also do SPL measurement as well. And that's also free. Many people who design home theaters and design movie theaters and all use Room EQ Wizard. Only thing it's not real time. So every time you need to do a new measurement, you need to take a snapshot of it, like a photograph of the measurement, which the software does for you. It's a little slower, but does the job very well. Is that clear? Any more questions? Athar had a question. Yeah. No, phase is a very, very complicated thing to get right. Okay, because every frequency has a different wavelength, obviously. Right, so you cannot get everything in phase, absolutely, because the thing is, you're not working in a room which everything is not going to arrive at and phase is relative to the position in which you put the microphone in. Now we'll check it in a bit. So if I'm standing here, I don't know if you guys can see me, but if I'm wherever I'm standing, wherever I'm standing now, if I put a microphone wherever I'm standing, okay, my relationship with the speakers will be very different. Like my relationship with the the back camera is on. Hold on. Yeah, no, I think the front camera should be on. So say for example, if I'm standing here, I have a particular relationship with the left and right speaker and the center speaker. But the moment like Atharva comes and stands there, his relationship with the speakers is completely different. So his ears and the speakers have a different phase relationship. Phase is always relative. Okay, you cannot have phase of one speaker. Okay, you can have phase of two speakers because you're considering one speaker and then the second speaker, you're comparing the two and seeing at which point are you standing, whether they're coming together in phase or no. So it's a very complicated thing. But if you understand the basics of it, you'll know exactly what can I compromise and what I cannot compromise. Okay, we'll look into it and just we'll do another 15-20 minutes of demonstrations. But at the moment, I hope you understand so much. Yeah. Any other questions? Are we good? Should we go in for demos? Okay, so what I'm going to do is, I hope you guys have headphones handy because it'll be great to listen to stuff on headphones. I have a mic right under my measurement microphone, which is what you guys will be listening to. Okay, so I'm hoping that whatever differences in phase and stuff happening, you should be able to make sense of that. Okay, so first thing first, let us understand how to read this phase trace, for which I'll need to sit down for a minute and run the whole thing for you guys. Any doubts you guys have?
No, sir.
Okay, just give me a minute. I'm just going to 3 and mix 4. Okay, so what I'm doing is I'm going to basically be playing some noise and I'm going to send that noise to 2 different auxiliary outputs, and we're going to try and I'm going to create a phase difference between the 2 outputs. Okay, can I have a chair? You all can see my screen, right?
Yes, sir.
Yes or no?
We can, sir.
Yeah.
Yes, sir.
Now let me just run you through the software really quick. Okay. So let me stop this measurement and let me delete this measurement. Okay, so the software is basically very simple to use. It's a free software and you can all actually download it and get it. Basically it's free, but you know, the guy takes donations. It's a Russian guy who's made it. And if you all want to donate something, you can donate. The iPad application is paid. It's I think some $5,000 something. So you have 3 different spots in the software. One is a main window where you can see all your readings. The window on the right is basically where you have a tone generator and your measurement microphones will all come in here. And the bottom of the screen is basically depending upon what you choose. For example, if I want to do some change of settings to the generator, then I'll just click on the generator here and all the settings regarding the generator will come. We can turn the generator into a pink noise, white noise, sine sweep, etc. Right now it's on pink noise. You can change the level as well, and you can also change the IO. Okay, so you click on any part of the software and all the settings regarding that particular section are going to turn up on the bottom of the screen. Is that clear?
Yes, sir.
So any question? Okay, so now what I've done is basically by default you have this one window here which has measurement. I click on that, then I click right here on this drop down menu here, and I can see what device do I want to use. So I'm using my Moto M4. Is that clear? Then you have the two inputs of the M4 that turn up here. You can see M and R. Is that clear? So M is the input that you want to measure. R is the reference input. So if you remember, if you understood what I told you earlier, my reference input is input number 2, correct? And my measured input, the input that I want to measure, is input number 1. Did you understand? So that's how the connections are. Any questions? Then you have a lot of other things which I want, which because I've not explained to you all this stuff, I'm not going to get into it. Just leave it default the way it is for now. Okay, you can also hit the store button and store whatever measurement you have taken. Okay, so I wanted taken one measurement by mistake. Then you have the window. What type of window do you want to see? This is a single window. Then you have a double window where you can see 2 different measurements together, and then you have a triple window where you can see 3 different measurements together. Okay, you have your phase here. Okay, I can take impulse response here. Let me get rid of this thing. Hold on. Okay, I can take impulse response here. Okay, and this can be, I'll tell you all what coherence and magnitude is in just a bit, but you can basically change the window. So this is the window I'm going to be sticking to for the most part of it. Any doubts here? Okay, there's nothing more in the software. It's pretty simple. I've told you how to do the connections. Also, I've told you what's on screen. Okay, so first let us understand what this whole phase trace is. I'm going to show you all a couple of things. Let's go to a single window and just let's put phase. And now I am sending signal to 2 separate auxiliary outputs. You all know what auxiliary outputs, right? So you're all budding engineers now, so you should know what auxiliary outputs are. I'm sending a pink noise to 2 different auxiliary sends, and I'm measuring the phase difference between those auxiliary sends. Okay, so that's what I'll be doing right now. Anyone has a question regarding that?
Sir, could you repeat that?
I'm sending pink noise on 2 separate auxiliary outputs, and I'm going to measure the phase difference between the 2 of them. So now see what I'm doing here. I have aux number 1, which is going to be my reference input. So aux number 1 is connected to input number 3. Okay. Then I have aux number 2, which is going to be the measure, which I'm going to delay, and I'm going to measure that guy. So that will be my measured input. That's going to be input number 4. Is that clear? Yes,
Sir,
no?
so this isn't through the mic, right?
This is not through the mic. I'm just showing you an example right now. So that's the reason why I changed the inputs. I'm having 2 separate auxiliary sends, aux number 3 from the console and aux number 4 from the console. Okay. So aux number 3 is is my reference, and aux number 4 is the signal that I'm going to measure. I'm going to measure the phase of aux number 4 compared to aux number 3 internally. Do you understand? Yes or no? So if I change this to an RTA, right? So an RTA, you should be able to see an input coming in aux number 3, aux number 4, input RI. Okay, aux number 3 is getting input. But why isn't it showing here? Because the measurement is off. There you can see, that's the pink noise coming on aux number 3. Okay, I'm just going to increase the gain slightly. Okay, why is it not coming? Input number 3 and 4, that's right. Okay. Just 1 second, I'm having a little bit of a problem here. Mix number 3, it's going at a level, okay, fine. Okay, something's wrong with the board's LED meters, no wonder. Just give me 1 second, guys. Something wrong with the board, I suppose. Just gonna change it. Let's go to aux number 3, mix number 3. Increase that. Okay, that's mix number 4, and that's mix number 3. Cool. Just check the connections from behind. I think we have swapped it. Hold on. Okay, aux number 4 is the measured guy. Yep, that's correct. Well, it's correct. It's correct. It's fine. Okay, so you'll see this thing here. So the meter down is basically mix number aux number 3 that is coming in, and this is aux number 4. You getting it? Yes or no? Guys, are you with me?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
So let me try this thing. So I'm going to go and go to the phase trace. The phase trace is going to be flat because both of these guys are absolutely in phase right now. Okay, and I'm going to try and delay one of these guys. Let's see what happens. Okay, so I've delayed aux number 4. So this is what happens. So now, if you can just get that iPad and show them what I'm doing here. So I'm comparing the phase of aux number 4 to aux number 3. Right now they're completely in phase. Okay, the moment I give a physical delay on the console, I've given it a 0.2 millisecond delay. Watch it now. What happens? Okay, you can see these lines. This is aux number 3 is 0 right now because 0 phase. But aux number 4 is getting delayed by 0.2 milliseconds. So you see these lines that are created. Now the thing is, you might wonder why is it, there is more delay here and there's less delay here because the lines are getting more and more vertical. The lines are not getting vertical because the delay is different, but we are on a logarithmic scale. If you see the scale down here, it's a logarithmic scale. Okay, look at the distance between 4K and 8K and look at the distance between 500 Hertz and 1K. It's the same. So obviously you'll see these lines are going to start getting vertical and vertical as you go higher in frequency. Okay, so this is with delay and this is the delay. So this is aux number 4 I've selected right now. The moment I put the delay off, they come back in phase. Are you guys understanding?
Yes, sir.
If you don't, just ask me. I'll explain the whole thing over to you.
So you're calculating. No, you're measuring this value in reference to the reference channel, right?
Yeah. So
Okay.
in this case, whatever is coming out of aux number 3 is my reference.
So over here right now, what's coming out of aux number 4 is in phase with aux number 3.
Yes, absolutely.
Okay.
Okay. The moment I put this delay on, on the console, I have a feature of delaying any output. So I'm going to deliberately delay aux number 4. The moment I delay it, I can actually see the delay on screen, and now I know, okay, fine, aux number 4 is getting delayed compared to aux number 3, which is at 0. Make sense? How many of you are getting it? How many
Yes,
of you are not
sir.
getting it?
Yes.
All clear, right? Yeah, so the gray line here is basically aux number 3. Is that 0 phase? But the blue lines that you see that are kind of changing in, they're getting more vertical as you go higher and higher in frequency. That shows that aux number 4 is getting delayed by a certain amount of time. Now you can see, like for example, frequency of 1K is basically out of phase by 105 degrees, minus 104 or 105 degrees is the phase difference between aux number 3 and aux number 4 at 1 kilohertz. Does it make sense? Or you all are like all confused and these lines are like, making you dyslexic? Is that the case?
So could you repeat that?
You can read on screen, right? 998.47 hertz is the phase relationship between that coming out from aux number 4 and the same frequency coming out from aux number 3 is about 104.84 degrees.
At that frequency.
At that frequency.
So that's why there are multiple lines. It changes as the
Yes.
frequency changes.
So as you go higher, the frequency changes. And this is about 4K, 4.5K approximately. Okay. The x-axis is frequency here. The y-axis is basically not time, not this thing. The y-axis is telling you the degrees. Okay, this is 0 degree, this is 45 degree, 90 degree, 135 degree. Minus 45 degree, minus 90 degree, means this is 270 degrees. And then minus 180 degree. You remember that thing, right? I told the cylinder cut from the 180 degrees and open it up into 2 dimensions. That's what has happened here. Okay, at this point, this frequency, 100 and whatever this frequency is, okay, 1.8K is 180 degree out of phase. That's the reason why it goes down here and and the circle completes from top again. This is called a wraparound. It wraps around this thing. So you can actually turn this into a cylinder. These two ends will meet if you were to turn this into one cylinder. Confused? Yes or no? Or okay?
Got it, sir.
So it makes sense now.
Understood? Makes sense?
Yes, sir.
I will completely understand if this confuses you. Because when I started learning this stuff, it was confusing. Cool, right? We'll go ahead. So you'll understand that the moment I remove the delay, now they both are complete. You can actually see them get in phase. Yeah. Yeah, I think you can share a screen there. So you can think of it like a slinky. You know the slinkies, right? Because I'll have to stop. Yeah. There you go. So can you, yeah. Are you guys understanding what I mean to say when it comes to the phase circle, right? Because if you understand that, then see, actually you can open that image, which is the 1, 2, 3, 4, 5, 6, 7, 8th image, the one, the colorful one, yeah, that one. Yeah. Are you understanding or confused? You need to talk to me. If you don't talk to me, I won't really understand where you guys are at.
Getting it, sir.
Getting it? Because see, this the problem here is that we are trying to imagine. First of all, are trying to visualize sound, which is very difficult. Okay, it is happening in 3-dimensional space, and we are viewing everything on a 2-dimensional screen. Okay, so it gets difficult for you to visualize stuff, and it will. I completely understand if you can't visualize it. So if you're having any problem, you can just let me know, and I will try another way to kind of explain it to you. You'll have to ask me a question for that. Okay, it is a slightly. I mean, we are heading into the physics domain part of things, though we are just scratching the surface. We're not even getting into the details of it. But still, if you'll have a question, I'm going to wait for a second. If you'll have a question, we can ask me. If you want me to repeat the entire thing all over again, we'll just go through it really quickly and try to make you understand. Should we go ahead to the next part? Did you understand phase and how to read that phase trace? More importantly, Yes,
Yes, sir.
or no? So now if you see a phase trace, you'll be able to read it, right? You'll know when this happens. You'll basically know when this happens. If you all know which is the reference signal, which is the measured signal, you know when this sort of thing happens, what is actually happening to the phase relationship, right? Should we go ahead? Next part.
Yes, sir.
Okay. So we'll have to do a couple of changes here. We'll go back to our measurement. Input number 1 and input number 2. So now I've gone back to whatever we did previously, where input number 1 is the microphone, which is getting measured. Input number 2 is the reference signal. Okay. So we're just going to do a small check. I'm going to switch my microphone off and I'm going to direct that Neumann mic into your headphones. So you'll have to tell me if you can hear it or no. Okay.
No, sir, we can't hear you.
Can you hear me now?
Can I speak? I guess
check.
they,
Yeah.
they can probably. Can you guys hear us?
It's very soft.
Very soft
Oh.
because I'm standing very far from the mic. Better now?
Oh yeah.
No?
Yeah.
Loud and clear, right? Okay. So I'm going to put my mic on and we're going to try and do a couple of things. Yeah, I'll put my mic off. You all can hear the noise?
Yes, sir.
So cool, you can all hear the noise, right?
Yes, sir, we can hear it.
Okay. So now what I'm going to do is I've shared my screen with you. You can all see the screen as well, right? Now I have a little bit of a scenario happening here. I have two speakers, left and right. If I think Atharva will spotlight my this camera. Okay, I have two speakers, this left and this right speaker, and if you see I have a center speaker as well. Okay? This is not like a LCR setup. I've done this particular setup just to give you an example. Okay, so what I will be doing is I will be so what I will be doing is when I play this speaker and this speaker together, you should hear a comb filtered sound. Okay, because of the distance, physical distance between these two speakers and the speaker, you will get a phase cancellation. We'll be able to even read it on the see that on the impulse response. And the moment I correct it, the moment I will actually have to virtually move these guys behind, not physically move them, but virtually move them behind. The moment I virtually move them behind, on the phase trace, on the impulse response, you should see them line up, and when you listen to it, you'll also hear a much more better low frequency response as well. Okay, we're going to try it, see if you can hear the difference. I'm sure you'll be able to see the difference. I'm not sure if you'll be able to hear the difference. It depends upon what headphones you're using and a couple of other things. So the first thing what I'm going to do is, let me you all can see my screen? You guys can see my screen, right?
Yes, sir.
Yeah. So what I'll be doing, the steps to do this thing, first of all. Now, you need to basically understand what are we actually doing here. We are trying to measure the time that it takes for the audio to come from these speakers to this microphone. At the same time, we are seeing how long does this speaker take to come to this microphone. Okay. Then what we'll do is, the next step is to try to align both the speakers so that we can hear it as one entire system and not like two different speakers, or three different speakers rather. Before this workshop, we made sure that these two are time aligned. We have actually moved them physically to make sure that these two are time aligned, and I can prove it to you. Hopefully if nothing has changed. What I'm going to do is I'm going to put one of the speakers off. Just pay attention on the screen, okay? So what I'm doing is I'm going to be muting my microphone. One speaker is off right now, okay? I'll play noise and we'll see one impulse here, okay? You see the spike? This purple color spike, I'm going to change the color of that. I'll delete this guy. Now this purple color spike is the impulse response of this speaker. That is the speaker on my left. Okay, if I'm facing my back, or rather if I'm facing the speaker on my right is what I have the impulse of that response. The impulse of that speaker is what I've captured right now. Okay, so I'm going to name it. Let me name it right speaker. It's R. Okay. So now I have my, what just went off? Okay. Now I have my, so now I know the speaker is basically, if I compare the speaker to this microphone, if I compare this whatever is coming out of the speaker versus what is being sent from the computer, there is approximately a 7 millisecond delay between the signal sent from the computer and the signal received by the microphone. Do you understand?
Yes, sir.
Okay. Matlab, when I play the signal from the computer, it is taking 7 milliseconds for it to go through the entire system and come out of the speaker and then reach the microphone. Make sense? Yes or no?
Yes, sir. Yes.
Okay. Now that is, I have calculated the right speaker. Now I'll also look at the left speaker to make sure that they both, now when I try to pick both speakers up, I need to make sure that both those speakers are reaching this microphone at the same time. So what I'll do is, now we have put the right speaker off and we have only put the left speaker on. I'm going to send the same noise. Okay, we have got a measurement. We've got a measurement, and let's turn that to a different color. Oops, wrong one. Okay, so now if you see this here, there's a very tiny bit of a tiny bit of difference here. So I'm just going to zoom into this section, which is from 5 milliseconds to about 8 milliseconds. So let's see if we can just take a look at that. 5 milliseconds and 8 milliseconds. Okay, so can you see this? The purple measurement is the right speaker and the green measurement is the left speaker. There's a very tiny bit of phase difference, which our ears won't pick out. It's hardly, it will be less than a millisecond also. It is like 0.01 millisecond of a difference. Is it making sense to you guys? Yes
sir.
or no?
Yes, sir.
So we know that now, we know that the right speaker is reaching 0.01 milliseconds prior to the left speaker. That's what it shows you. And when you compare both the speakers to what the system is sending, there is approximately a 7 millisecond time delay between them. Make sense? Yes? No?
Yes, sir.
Because there's a tail for the impulse response, because the room also is adding to this thing, right? So you'll see all the sustain of the room as well. That's why there's a tail, it's not a spike. If you were in an anechoic chamber, it would be one line. Okay, this is because we are not in an anechoic chamber, we are in a live room and it has got a tail to it. Do you understand so much? Yes or no? Speak to me.
Understood, sir.
Okay, so now what we are going to do is, we can take care of it, but it does not really make a difference because it's 0.01 milliseconds. Our human ears won't be able to pick out the difference. Okay? So when I play both of these guys together, on that Neumann microphone, it sounds something like this. I'm going to switch my microphone off. You'll hear the noise. This is when the left and the right speaker are playing together. Okay? Good to go?
Sure, sir. Can we get the impulse while playing both the speakers?
It won't make any sense because it will just show one spike only. We can take it, it'll just show one spike. I'll take it, okay? If you want it, I'll just take it. Okay, so that's what it looks like together. You'll see this, okay, now you'll notice if someone asks me a question, right, why do we have that tail? When both the speakers are playing together, see where the peak comes. It comes in slightly delayed. And then there's a tail to it. Because now you're having two speakers, right? You're having two speakers with, one speaker has the, the speaker left, it has a difference, has one relationship with the wall on the left, and the speaker right has a different dimension with the wall on the left. So now both these reflections are going to arrive at different times to the microphone. So you have a slightly different, if you compare all of them together, you can compare these three readings, see how different they are. Right? You see the, this is the left, green is the left, okay? This purple is the right, and the last one, blue one, is a trace of both together. And you can see the difference between all of them. Okay, it's not a difference that our ears will make out. The software can, but our ears won't make out that difference. Such a tiny difference. Should we go ahead?
Yes, sir.
Yeah? Okay, coming to the last part. Let us get rid of all this. Now I'm also going to play the center speaker to you guys. Okay. Can you hear me? Okay, it's not. You guys can hear me?
Yes, sir.
Yes, sir.
Okay. What I played just now is the center speaker. This is the main speaker. Okay? I'm going to play both together now and see if you can make out a difference. Apart from the level change, apart from the level differences, apart from level changes, can you make something else out when both the speakers are playing together? You want me to play it again for like 30 seconds or so? Just get me the headphones. Let me also listen to what's coming out of the board. Do you all make out the difference? Okay, I'm going to try and listen to it myself so that I can gauge it. Does it sound any different to you guys? Does it sound any different? Can they hear me? I'm not sure if they can hear me.
No, sir.
Sounds the same, right? Because it's noise. So what we'll do is I'm going to take some readings. Check. Okay, is mute. Yeah. So there is a difference, but you're not able to make it out. So what I'm going to do is we're going to take some readings. Okay. So let us first, what we need to do, our reference has to be, we want to move this main system virtually back to the center. Okay. So let us first see where does the center speaker lie in space, basically. What is the relationship of that with respect to what we are sending it? So I'm going to switch my microphone off. Okay, so this what I just took here right now is the center speaker, which is approximately 9 milliseconds, 9.5 milliseconds. It's delayed by 9.5 milliseconds compared to what is been fed to it. So computer से उसका delay है 9.5 milliseconds. Okay, and we already measured our main system, which is, let me turn this to single. Okay, so this is where this blue trace is where our main left-right speaker is, and this orangish thing that you see, impulse you see, is your center speaker, right? मतलब ये blue trace जो है पहले आ रहा है, उसके 2 मिलीसेकंड बाद आपको center speaker सुनाई दे रहा है. Does it make sense?
Yes, sir.
Means that the
Yes.
relationship between this speaker and this speaker is 2 milliseconds. So if you are standing where the microphone is, when you heard that Neumann microphone, you basically heard both the speakers together, but there was a time difference of 2 milliseconds between them. Does it make sense?
Yes, sir.
Yes? So now what we need to do is we need to try to make sure that it sounds like one system. So before we do that, what I'm going to do is, just for reference, I'm going to play some music, okay? And I'm going to play some music that is a little vocal centric, so that you can hear what it sounds like without giving the delay and after giving the delay. Because with noise, it's very difficult to make out, right, what's happening and what's not happening. So I'm going to play a song that is a little more vocal driven. Let me go to... So you should be able to hear this song. Can you hear the music? Yes or no?
Sir.
Boys, boys don't cry. Boys, keep it all inside. I try
Okay, sir.
to hide it underneath. Still my heart starts to beat. My human heart only got a human heart. I wish it didn't run away. I wish it didn't fall apart. Oh, my human heart. Night and day, and light and dark. Anything it could be torn in half. Only got a human heart.
Girls can make believe. Girls wear it on the sleeve. Thought I could pretend for trying sake. Still my heart had to break.
My human.
The music? Yes or no? Guys. Are you there?
Yes.
Okay, you could hear the music, right?
Yes, sir, we can.
Okay, so that what you are hearing is you were hearing it through that Neumann microphone which is placed between the two speakers, and you could hear only the left-right signal right now. So I'm going to now slowly fade in the center speaker and see if it, just try and make out if you can hear some change in it. Okay, whether it sounds better or worse or whatever. Okay, I'm going to try and monitor what I'm listening to. So as I'm going to play the main left-right speaker, and then I'm going to kind of blend in that center speaker. Okay.
Keep it all inside. I tried to hide it underneath. Still my heart starts to beat. My human heart only got a human heart. I wish it didn't run away. I wish it didn't fall apart. Oh, my human heart. Night and day, and light and dark. Anything could be torn in half. Only got a human heart.
Girls can make believe. Girls wear it on the sleeve. Thought I could pretend, for trying sake. Still my heart had to.
So I put in both the speakers, okay? You may not make out a difference, okay? It's very hard to make out a difference, but now let's kind of pull them both in time and see if we can make out a difference after we pull them in time, okay? So we have a difference of about 2 milliseconds. So let me, can you show this thing here? On my board, I'm going to dial in a delay of 2.3 milliseconds, okay, which is already dialed in. So on the main, this is my main output. I've dialed a 2.3 millisecond delay, and now let us take another reading and see whether anything had changed. Okay, this is the main system again. Okay, the main, and let's put in the center as well. Okay, so they've closed it up now. Can you see that? This is the center. This is the main, correct? Now when you put them both together, there is still about a 1 millisecond delay, which we'll try and get rid of. So let's see if we can get rid of that. No, I can't get rid of it because unfortunately the board lets me only move from 2.3 milliseconds to 2.6 milliseconds, which then delays it further. So this is the best resolution I can get with the delay dialed in. Are you all making the difference? I mean, are you all understanding what is happening here?
Yes, sir.
Yeah?
Yes, sir.
So now, so what I'm going to do is now I'm going to play the music and going to put the delay on and off and see if I can make out any difference that's happening in the audio. Okay? So
You put a delay on the send, right?
Sorry?
You put a delay on the send to the center.
I've put a delay on the mains because the center is behind, right? So I cannot get the center ahead in time. I have to put them.
Oh, yeah.
So I've
Okay,
pushed them
got it.
behind. So let us see now that we know that, okay, fine, they seem to be aligned. At least this is the closest we can get. But does it make a difference on the audio part of it? Let us see. I don't know if you guys will be able to make it out, but let's try. Okay, I'm going to put my mic off. Okay, so the music is on. I'm going to keep swapping the delay on and off and see if we can make out a difference, okay? So this is both the speakers on right now. I'm going to mute my microphone and keep playing with the delay. So see if you can make out a difference.
underneath. Still my heart starts to beat. My human heart only got a human heart. I wish it didn't run away. I wish it didn't fall apart. Oh, my human heart. Night and day, and light and dark. Anything could be torn in half. Only got a human heart.
Girls can make believe. Girls wear it on the sleeve. Thought I could pretend, for trying's sake. Still my heart.
Any difference that you can hear?
There's a question. So how do you
Yeah.
insert the delay?
It's the delay has been inserted on the console. I'll show that to you. But moreover, can you make out any difference in the audio? I mean, I'm not sure over the internet and stuff, right? What can you actually hear? But if you all notice very closely, the vocals and stuff should get it should get a little more fuller basically. Even though you're listening in mono, you should get a little fuller. So when the delay is off, it should sound a little filtered. When the delay is on, it should sound a little more fuller. Anyone make that observation, or you all can't make out anything? Someone needs to speak to me. अगर कुछ नहीं सुनाई दिया तो बोल दो नहीं सुनाई दिया. I can understand. Yes or no? It's a little difficult for me to
Can't find
understand
much
headphones
difference.
because I'm hearing to the speakers by themselves and the headphones, so it's a little confusing for me. But I believe for you guys, you should be able to make out some difference. If you all cannot hear the difference, but you can at least see the difference on the screen, right? When
Yes.
this is the main and the center after giving the delay, and this is the main and the center before the delay. How I've given the delay is on the console, on the output of the main output that is going to the left-right speakers. I've basically given a 2.3 millisecond delay. Does it make sense? Because that gets us to the end of this whole session.
Are there any questions taken up?
If you have any questions, you can quickly ask me. Even if I have not answered anything, you can ask, you can tell me.
So would this be used in studios for multiple monitor setups?
Absolutely. Very, very essential. To do SPL and to do phase sync. When you have not multiple monitor setup per se, but when you're setting up a left and right monitor, right, to make sure that at the sweet spot they're in phase. So you need to place them right. Otherwise you might get a smeared image. So when this is done before when they're building the acoustic treatment of the room. So we did not actually speak about the magnitude trace and all, because if you speak about the magnitude trace, that is much better than the RTA that you see for room measurements at least. We don't have enough of time for that, and I think I've confused you enough to at least, hopefully this whole session would at least give you a slight, at least an introduction to what this whole measurement game is all about. This is just an introduction. If you all are getting confused, it is very, very natural. Okay, there's nothing, it's okay, because sometimes it does get a little overwhelming. But this is just to show you that this is a very, very vast field, and if you all have the knowledge about using an FFT, or at least have an understanding of how audio works in air, it will give you a much better understanding of how your mix would translate from one room to another, how to set up your own room. Okay, we have not gone into RT60 measurements or not, because we need more sophisticated softwares than Open Sound Meter to do RT60 measurements and stuff like that. But you can get an idea of what happens by looking at just the impulse, what the RT60 would be like. So anyone wants to ask me any question? Did you guys understand the last little exercise we did? I'm really not sure of what you could hear, what you couldn't hear, but it is quite evident on the screen at least. And which is also a testament of like, even if you can't hear things, if you know how to measure it right, you can actually see the things on the screen and you can make decisions by looking at them and then developing your hearing and to picking out how things hear. See, whatever you see on screen is great, okay? But it should also translate in air. If it does not sound good outside, there's no point of using all this setup and to try to figure out and treat your room and stuff like that. So whatever you do on your computer, the last person to judge is you. Whether you like it when you hear it or not. If you're not liking it when you're hearing it, means whatever you've done, there's some fault somewhere. Okay? So after doing all the exercises, you need to listen to your system and see, okay, is this what I really wanted? Okay?
So what if you're in a situation where we're calibrating live sound, but we are in a control room?
Okay, calibrating live sound and you're in control room, which is a very, happens, it does happen. So it'll go off. You can, so what you can do is, what you can do in that case is first of all measure what's happening outside, okay, in your in the main PA system. Try and get a speaker system that sounds similar to the main PA, if not exactly the same. Okay, it should sound at least similar. Then you need to set up the delay, because even if you are in a control room, you might have a wall. That wall might not be enough to stop the low frequencies from leaking into the room. And then when you put on your control room speakers and put on the main PA system, you'll hear like a delayed sound. You'll actually hear echoes coming in. So in that case, what you need to do is you need to basically time delay your near field speakers to the main system. And that's when you'll use something like this. You put a microphone where you're standing, you play your main speakers, play your secondary speakers, and then find the time difference and delay your secondary speakers to the main speaker. So when you play both the speakers at the same time, you will now not feel as if there's a time delay. Okay, so it would be much more clearer for you to, it will be less annoying for you on the ears at least, because when you're hearing the same sound from two different speakers, it gets very annoying for you. You can't make out what's happening. So you'll have to basically put a microphone at your control room position, measure the distance of the, or else even if you don't have this, even if you don't have all the setup, you can actually take a laser measurer and basically measure the distance between you and the control room speaker and you and the main PA system, and then find the distance in feet or meters and dial that distance in. Okay? Does that answer your question?
Yes, sir. Yes.
Yeah. Anyone else?
Also, when the design, placement of speakers will come in designing the stage, right?
Yeah, to an extent.
So,
how much space you have, yeah.
What if it's an impromptu setup?
Impromptu setup, then you basically figure out where you're going to put your system in, and then place in your microphones and start measuring stuff.
And with that, would we be moving speakers around?
You cannot move speakers around. No, once it's set up, it's set up. And you're not going to be taking measurements from one position. You have to take an average. It's all about taking averages. I've not gone into depths of the acoustical crossover point and this and that, because there's a way of setting things up. Because you guys are online, so you can't really experience stuff the way we are experiencing it in the room. For you to understand what is an acoustical crossover point and stuff, you'll have to be in the room with me, so that you can actually feel it. But this whole exercise was just to give you a glimpse of what is there in the measurement world. It is by no means to tell you how to use stuff. If you want to understand stuff, you can download Open Sound Meter. You'll have, you now have understood how to do the connections. Even if you do not have a measurement microphone, you can do impulse response measurements. You can do time delay measurements by using any microphone. Okay, you can't do an RTA and stuff, but you can at least measure the distance and stuff, right, with any microphone. It can be an SM58 also. As long as it's a microphone, you have an interface and you have Open Sound Meter with you, you can do measurements. You can take two different speakers, put them in two different distances, and you can place a microphone somewhere between the two speakers and figure out what the time difference is. So that practice you can do with any microphone. Okay, you don't need to have a measurement microphone for that. Okay, the software, just Google the software Open Sound Meter. You can download it. It is very, very easy to use. If you have even understood 10% of this class, right, you should be able to figure things out by yourself as well. Any questions? Anyone, anything, anyone has not understood something or is completely lost? in the world of time and space and whatnot. We're good?
Yes, sir.
Okay. Again, one last time, if anyone has any question, just quickly shoot, or else then we can conclude the whole workshop.
So
Yeah.
how does this work with line arrays when they're curved?
The whole curvature of a line array is decided by a software, by a different algorithm.
So all of this would be set in that software.
No, not really. So that uses the same principles of impulse and stuff. It uses the same basic math. And using that math, using the data that you have fed into the system, it will give you the optimum splay angles for the system. Okay, then where would you use this when you're using a line array system? To make sure that whatever you have done in the software is actually translating in the real world or no. Right? So you have set up for 2-3 days, you sat, you put on all the dimensions of the venue you're working with, everything you put in, and you've come up with this whole report of whatever you want to put up. You have put up the speakers also according to what the software says, everything. But now, when you listen to it, you have to make sure that whatever you have got on paper is also happening on the field, right? So that's where you'll use this microphone, you'll use this system, and you'll verify what the prediction said and what is actually happening in the field, and then you'll make decisions based on that. Okay? So 95% of the work is done by the simulation software of whatever brand of PA you're using. But the last 5% is what you need to do on field. Okay? So maybe the temperature changes, something changes. You need to optimize the system. That's where you'll go in, and the whole optimizing of the system is done on maybe on different hardware and different software. So in this kind of a scenario, 2 or 3 different worlds come together. If this is very, very important when you're setting up more than live sound. I would say this is very important when you're doing sound install. Because when you're installing sound, you need to know how to take an impulse response reading. You need to know how to time delay certain speakers. Say you're setting up a auditorium and you are having, like different speakers in different zones, right? You have one main PA system, and then there are some seats way up in the balcony right behind, and you need to put smaller systems in those zones to cover up. So you need to basically, probably are working with 30, 40, 50 speakers in like some 50 zones, and you need to make sure all of them are time aligned. So when you play something from maybe some music is played or someone starts performing on stage, you should not be hearing different speakers from different locations, no matter where you stand. You should be hearing a cohesive sound, and that's where time delay and measuring all this phase response and all comes into play. Not only that, whenever you're setting up the room, when you're doing acoustic treatment for the room, you need to know what are the standing frequencies, what are the standing waves in the room, what is getting cancelled out, what is getting doubled up, where the bass traps need to be installed. Most of that data you will get when you just put a room dimensions. You can calculate the basic standing waves when you put room dimensions in. But what about the harmonic and the harmonic frequencies? Right? So all that information is much more easier to get using a setup like this rather than sitting and doing it on pen and paper. Okay? So it's not only for live sound, it can be done when you're setting up acoustics no matter where you are. You can use a simple software like Room EQ Wizard or Open Sound Meter and do a very simple setup and understand what's going to happen once you place speakers somewhere in the room. Okay? So making sure that whenever you're sitting in the sweet spot, both the left and the right speaker, you're sitting at a point where both the left and the right speaker meet exactly in phase. Not one speaker is in front of one, not one. And it gets all the more complicated when you're doing Atmos setup or when you're doing a 5.1, 7.1 setup, when you're setting up movie theater and stuff. So all this time delay is like very important because when you're using multiple speakers. Okay, and then SPL also to make sure that everything is playing at the right SPL. Okay, it's a complicated dance basically, and it requires practice to get it right. Any other questions? So we are good?
Yes, sir.
Okay, so we're going to roll out some feedback forms. Just make sure that you fill those in and you send them back to me so that
Sir, can you repeat the name of the softwares you just told?
Open Sound Meter. I think Atharva can just type it. Just Google it and you'll find it. It's a free software. It works on Windows, Mac OS, and Linux. Okay, any other questions? We got good, right? All right. I am going to, if you have any more questions and stuff, and you have any doubts, you can also email me. You can find my email on EduCloud. At any point, if you feel that you missed out on something or did not understand anything, just give me a ping on the email. Yep. All right, guys. I will see you in class soon.
Thank you, sir.
Thank you.
Thank you, sir.